Hello everybody, welcome to Lab Hours. Welcome to the first mini lecture in the Econ 378 mini lecture series. This one is Probability and Combinatorics. My goal with this mini series is to be able to give you just a 15 to 20 minute recap of what the lecture was, three topics that I think were most important about the lecture, and just a quick review of those topics and the ways that I think about them to try to remember them. I'll try to give you the math behind them and also try to give you the intuition behind them. And we're going to call each of those three ideas the Tommy Triple for each of these little mini lectures. Now, of course, I got to give thanks to Professor Jensen, who has put this curriculum together. I've helped with it, of course, but she gets that from other people as well. If you are currently in the class, this video assumes that you have attended lecture and that you have a basic idea of what we're talking about here. If you're not in the class, this mini lecture presumes you have a basic understanding of the notations of set theory, like union, intersect. I actually don't use an element of, but things like union and intersect, and just the idea of set theory in general, how we're going to relate this to probability, and so on and so forth. So if hopefully with this mini lecture, if you're reviewing for a midterm, or if you are just trying to get some help with a concept that you don't quite understand on the homework, this can be a good substitute for if you can't make it to lab hours, or if you want to supplement your lab hours attendance with this. Hopefully this little virtual set of lab hours is going to be helpful for you. So let's jump right into our first item here on the Tommy Triple. Let's just really quick go through. We have total probability, independence, and combinatorics basics that we're going to work through. So let's start with total probability. And the total probability idea is as follows. The probability of A intersect B is equal to the probability of A plus the probability of B minus the probability of A union B, and vice versa, that the probability of A union B is equal to the probability of A plus the probability of B minus the probability of A intersect B. Now, we know this is the math. This is just a formula, right? If I were to give you, probability of A is equal to 0.6, and probability of B is equal to 0.2, and probability of A intersect B is equal to 0.1. First of all, I would point out that all of these probabilities are reflecting a sort of grid, right? Or let's just do this, and let's divide it into 10 pieces, okay? That's what, 6, 7, 8. That's too many. No, it's not. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's say this universal set has 10 equally sized boxes. Let's pretend that these are equally sized, right? So each of these represents 10%, even though I know that that's not quite the case, right? Let's call this the universal set S. And let's say 6 of these boxes then would be A. And let me actually highlight that so that you can see it, right? Let's call A the blue ones, and 6 of these boxes would be A then, right? If this is our universal set and these were equivalently divided, which again I realize is not necessarily the case, but hopefully you can bear with me for that one. And then the probability of B is 0.2, which means 20%, but we also know that the probability of A union B is 0.1. So one of these boxes is both A and B, and 2 of these boxes are B, and 6 of these boxes are A, so I could draw that like this. Again, assuming that these boxes are equal. This fulfills the criteria, of course. Probability of A is equal to 0.6. Probability of B, and then the probability, of course, of A intersect B is just going to be wherever those touch, right? So, again, I can point out to you, assuming these boxes are equal, the probability of A is 0.6. 1, 2, 3, 4, 5, 6 out of the 10 boxes. The probability of B is 0.2. We have 2 boxes out of the 10, of course. And then the probability of A intersect B is 0.1. Just 1 out of the 10 boxes, of course, right? So let's talk about this. What is the probability of A intersect B? It represents everything that is covered both by A and B. If I were to call this universal set S a dartboard, and I was just to fling darts at it, then I would maybe want to know, hey, what percentage of the area of this dartboard is an A hit? Like maybe I'm a professional darts player and I need to hit A to win, or I need to hit B and avoid A or something like that, right? So I throw my dart, it lands here, right? Oh, cool, I just hit B. That means I must be in this square. Cool stuff. I have a 20% chance of hitting B if I just close my eyes and fling it because I'm a pro, basically. A intersect B is pretty easy to understand from this diagram. I also think that A union B is pretty easy to understand from this diagram. It's just everything on the dartboard that I can hit that is either in A or in B, or in its intersect, because that would necessarily be in one of A or B, of course, right? That's why you'll sometimes hear union referred to as the, not U like a U, but union is referred to as like the or, although that sometimes can get a little bit confusing because English is a little bit funky sometimes. So we see this, we understand this intuitively, right? This probability, let's just say, what is the probability of A union B is equal to question mark. And let's just highlight it here with the, the green. Why not? Let's call it green. So this green highlight is just going to go over everything where I hit either A or B, of course, right? Boom, 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 boom. Highlight that. Ka-chow. Great stuff, but that green is a little bit ugly. So now you understand kind of the intuition of the union. Let's show how this works in the math. Well, if I take the probability of A, in fact, let me just do the laser here so I don't have to write it again. I have the probability of A intersect B, I have the probability of A, I have the probability of B. That means I can probably find the probability of A union B. And I'm not going to use this equation, I'm actually just going to use this equation. You can see that adding this to this side and subtracting this to that side will give you this bottom equation here. So let's plug it in. Probability of A union B is equal to, first, the probability of A, which is 0.6. Then second, the probability of B added to it, which is 0.2. And then, of course, we need to subtract the probability of A, the other thing, B. In this case, the other thing is intersect. So we are going to subtract 0.1, and that is going to leave us with 0.7, of course, because this is 0.8 minus 0.1 is 0.7. And you will notice, hopefully, that this green highlight covered 7 of these boxes. Wow, that's pretty crazy. That's about all that you really need for this. I'm going to be honest with you. Like, this is as difficult as it gets here. Just remember these formulas up here, and just this general idea. The universal set is a dartboard. I fling the dart. If I need the union, what is the chance that I hit anywhere that is A or B? If I need the intersect, what's the chance I hit A and B at the same time? And then A, B, pretty easy from there, right? So let's go back. Let's check off total probability. First element of the Tommy triple is done deal. So let's now get into independence. This one is a fun one. Independence mathematically suggests that the probability of A intersect B is equal to the probability of A times the probability of B, if they are independent. So this is like a check. This is like a definition. If this is true, A and B are independent. If this is false, they are not independent. So we understand this mathematically. This is actually no more difficult because we have all of this. So let's just get the intuition. I'm going to draw you 2 dartboards here. This one is a square, right? Let's call this S1. And then we draw this square over here. Hopefully it'll give me a square. Cool. And we'll call this S2. And the way that I'm going to divide them is I'm going to put this line down the middle here, and I'm going to put this line in this little corner here. And what we're going to do is we're going to say that this blue line divides A from A complement, or A and not A. And same thing goes over here. We've got A and we've got not A, right? So let me just really quick go ahead and give those a highlight so that we stay clear which side is A, okay? Here we go. And over here we'll put it in the box. Again, we're going to treat this as like a dartboard, okay? And while I'm drawing this, the basic intuition of independence is that if you tell me one thing about A, and it doesn't adjust what I think the chances are of me also hitting B, the two things are independent. If giving me information about A doesn't give me any more information about B, they're independent. So let's just continue. Let's do this really quick. I'm going to draw the same B line, and we're going to assume that it's halfway down the square. All right. Again, we're going to assume a couple things here. Okay. On both of these squares, right? So we have B on the top and B complement on the bottom, B complement, okay? And let me just go ahead and highlight the B sides really quick. Okay, easy peasy. I'm sure I'm shaking the camera a little bit. Hopefully that doesn't bother you too much. Okay, let's go ahead and do that. Okay, so what is the and let me just call this A1 and A complement 1 A2 and A complement 2, and then the b's are the same across both of them, so it doesn't matter. So the question is A1 independent from B? Is A2 independent from B? Well, let's find out. Assuming that I've drawn this to scale, which is something you're going to have to do to be nice to me, let me make these a little bit smaller now that I've drawn them so that we can kind of do some math around them. So in set 1, the probability of A, I have tried to split it in half. We're going to treat that as equal to 50%. The probability of B is just always going to be, so let's call that probability of A 1. Probability of B is always going to be half in this setting, right? And so we can also see that the probability of A intersect B is equal to 1/2 times 1/2, or a quarter, right? It's a quarter up here in set 1. So the probability of A1 intersect B is equal to 0.25. So A1 independent, independent of B, question mark. Hopefully you can see that the answer is yes. Our equation is if the probability of A times the probability of B is equal to the probability of A intersect B, which is true here, 1/2 times 1/2 is equal to 1/4, then A1, yes, is independent of B. Great stuff. You've seen the math. Let's make the intuition a little bit stronger here. If I threw a dartboard at S1 and I hit B, does it give me any better or worse chance of also having hit A? For example, I blindfold myself as the dart thrower, I throw the dart, I hit S. You tell me I hit B. Does that tell me anything new about whether or not I hit A? The answer is no, because whether I hit B or I don't, I still know I have a 50% chance of also having hit A. That was also the original probability of hitting A, so you basically didn't tell me anything about A in this first dart throw. Now for the second dart throw, this may not actually be the case, right? So let's take a look at this. S2, the probability of A2 is only equal to 1/4. It's only this 1/4 right here up in the top left corner. The probability of B, of course, what a B. The probability of B, of course, has not changed. It's still 1/2. And the probability of A2 intersect B, fun fact, is also equal to 1/4, just like it was above. But the question is A2 independent of B? Hopefully you can tell that the answer is no, because probability of A times probability of B is 1/4 times 1/2, which is 1/8, which is not equal to 1/4. A2, no. And again, let's just solidify the intuition here. If I threw a dart at board S2, blindfolded, and you told me, hey, you hit B, what does that tell me about whether or not I hit A? Well, the cool thing is, if you had told me that I had missed B, I also know that I missed A. Whereas if you didn't tell me anything about B, I don't know if I missed A. That means when you tell me about B, you're giving me more information about A, which means these things can't be independent, right? If you tell me I hit A, that means I also had to have hit B, because it's impossible to hit A and not hit B. And so you'll notice that these two things can't be independent, because if you tell me, the blindfolded dart thrower, hey, you hit A, then I can go, oh, that means I definitely hit B. Whereas if you don't tell me that I hit A, I only have a 50% chance of having hit B, right? So the intuition behind independence is if telling you something about the one also tells you some new information about the other, they aren't independent. The classic example of this is 2 coin flips. If I flip 2 coins and I tell you the first one was a heads, does that help you in any way to know what I flipped on the second coin? Absolutely it does not. But it does tell you what happened to the first coin. I hit heads and I did not hit tails, which is to say I hit A and I did not hit A complement. So those two things are mutually exclusive, flipping heads and tails in 1 coin flip, but flipping 2 coins and getting heads is actually independent. So that's the whole thing. It's pretty cool. Mutual exclusivity, independence, fairly unrelated, just separate things, okay? So that's a common misconception that some people could take. That's about all we'll need for independence, so let's check that off the Tommy triple, and we're gonna go into the Combinatorics Basics now, which is basically just gonna be a couple math formulas. So if I have a group of n things and I need to pick groups of k out of that group of n, the formula for that is n factorial over k factorial, n minus k factorial. Great, that's a formula. What the heck does it mean? So let's think about this for a second. Just n factorial in general is the idea that if I need to pick something, I only have that many things minus one ideas left, right? So if I have 3 books and I want to know how many ways are there for me to how many orders are there in which I could read this book, right? So in which I could read these 3 books. So I could take book A, I have books A, B, and C. N factorial says if I pick A first, then I could go to B to C, or I could go A to C to B, right? If I pick B first, I could go, A to C, or I could go B to C to A. And then, of course, if I pick C first, I could go from C to B to A, or I could go C from A to B. Notice, please, for me, will you, that we have 3 different options here. And then for each of those 3 options, we have 2 options in the next slot. And then after that, there's only 1 book left for each of them. Okay? So this is the idea that n factorial is equal to 3 times 2 times 1 is equal to 6. Please notice 1, 2, 3, 4, 5, 6. Ka-chow. That's what a factorial is. Okay? How does that actually help us with combinatorics? Let's talk about that for a second, okay? So, n pick k. Let's say, for example, I have these 4 boxes, A, B, C, and D. Okay? And I want to know how many different groups of 2 boxes, or even of 3 boxes. Let's say, how many different groups of 3 boxes can I make from this group of 4 boxes? So, let's check it out. I could go A, B, C. Okay, that's bad. I could go A, B, C. That's 1. A, B, C. I could go A, C, D. That's 2. I could go A, B, D. That's 3. I could go B, C, D. Does that cover everything? I think it does. C, A, B, we covered that one, we covered that one. That's pretty cool. There's only 4 different groups of 3 boxes that I can make from this group of 4. That's pretty cool, right? Maybe I could highlight them like this. Shoom, and then shoom, amogus. Shoom, and then shoom, right? Pretty cool. Not super helpful, but let's talk about that. 4 different ways that we can make a unique group of boxes. And in this case, we don't care about order. I just want to pick people, right? Or pick boxes. If I plug this into the numbers, n here is the total number of things I have, so that's 4 factorial over, and k is the number of things I want to put in each group. So in this case, that would be 3 factorial, 3 for k, and then n minus k is 4 minus 3 factorial. Now, let's make this super simple, right? The really cool thing is that 4 factorial is 1 times 2 times 3 times 4, and that will be over, parentheses, 3 factorial, which is 1 times 2 times 3, times 4 minus 3 factorial. 4 minus 3 is 1. 1 factorial is 1. So let's do this really quick. 1's cancel out everywhere because of the identity property of multiplication. These 2's will cancel, and these 3's will cancel, and we are left with 4. Ka-chow. Would you look at that? Super cool. So that is how the math works, but let's think about this in a little bit more of a real-world example, and I'm going to stretch the definition of real world here for this one. But let's think about this in an example where I want to use combinatorics to give me probabilities instead of just like combinations, right? Because that's cool that I can pick 4 different groups of 3 boxes from a set of 4 boxes, but how helpful is that really in statistics? Well, let's talk about the way that it can be helpful in statistics, which is this combinatorics thing, right? So let's say, for example, I will give you this hypothetical, and I'm pushing 20 minutes, but hopefully you won't mind that too much. So let's say, for example, we have 13 gamers and 12 ballers in a class of 25 students. And at this school that we go to, the really cool thing is that student council is actually determined by a random draw from a little hat. right? Let's just draw the little hat here. What a hat that I've drawn. They draw names out of a hat to assign 10 spots on the student council. It's just random. People are like, we don't want to do elections. It's a whole thing, yada, yada, right? Let's say that these 25 students are randomly assigned to 10 spots on the student council, or at least it's supposed to be like that. However, one thing that happened this year is that you found out that 9 gamers actually ended up on the student council. And you say, that seems a little bit fishy. All right, there's about as many ballers as there are gamers. It seems really crazy that we would have randomly gotten 9 gamers onto 10 spots of the student council, given what the class looks like, right? So you might be wondering, well, what is the actual probability that this sort of things does actually happen randomly? Like, what is the chance that somebody actually stuck their hand into the hat 10 times, pulled out 9 of the gamers' names, and that's just what we had? Or maybe you're a little bit suspicious of the gamers, and maybe you think they might have rigged the hat pull. So let's just take a look, all right? How can we use this as a general probability thing? Well, the first thing that we need to do is we need to establish some kind of universal set. And in this case, that universal set is going to be the number of ways that you can randomly assign 10 students to the spots on the student council from the 25 in the class. Those are all of the possible unique student council makeups that we can have with this class of 25 people, right? So we have 25 students picked for 10 spots. This number you recognize is going to be quite large, hopefully. There are lots of different groups of 10 you could pick from a group of 25. So, but what do we do about the top? Well, let's think about that. If I just want to know the probability that we get 13 gamers into 9 spots, or that is to say, if I just want to know the number of different ways there are to get 13 gamers into 9 spots, well, that would be easy. I would just do a 13 pick 9. I want to pick from the 13 gamers. I want to give them 9 spots. And then I also just want to I want to take the 12 ballers and I just want to put one of them in one of the spots, right? So I have 12 ballers up here on the top, and I've assigned them to one spot. Hopefully you notice at this point that this number is just equal to 12. It's 12 factorial over 11 factorial times 1 factorial. 11 factorial is going to cancel everything out, just like 4 pick 3, 12 pick 1, or 12 pick 11 are both going to give you, 12, which is great. And then you say, okay, I can actually multiply these together, right? Because this is the number of ways that I can assign all of the gamers so that this is true. And then for each of these ways, I could assign one of the 12 ballers. So that gives me 12 different options for this specific scenario of student council for every group of 13 pick 9 from the gamers, right? So we're going to multiply these on the top, and we're just going to do the math, and we're going to say, okay, this should give us a probability because this number should be smaller than this one, because this is a really specific way that the student council can come out of the hat, and this is every way the student council can come out of the hat. So let's do the math really quick. And let me move it so that we have a little bit more room, and then we will be finished with the lecture. But 13 pick 9 is equal to 13 factorial over 9 factorial times 4 factorial. 13 minus 9 is 4. Times 12 factorial over 11 factorial 1 factorial. All of that over 25 factorial over 10 factorial 15 factorial. Great stuff. Excellent stuff. I'm going to bring up my little calculator that I've got here so that we can actually do this math. And I believe it does factorials, right? Gorgeous. Okay, so let's just do 13 factorial over 9 factorial times 4 factorial, right? And now you could write this out as like 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8 times 9. Realize that the 9 cancels with the first 9 from the 13, and then it would just be 10 times 11 times 12 times 13 over 1 times 2 times 3 times 4. That's super easy, but we're running low on time, so I'm just going to crunch these shortcuts here. And in fact, let me resize this and move it over so that I can actually do a little bit of an equal sign writing. So that is 715 times 12 pick 11 and 12 pick 1 are the same. They're both going to be 12. I hope you can trust me on that. And then luckily, we've got this 25 factorial. Good thing we've got this calculator because this would have been obnoxious to try to figure out. This is 3,268,760. 3, 2, 6, 8, 7, 6, 0. I can come back over to my calculator. I can do 715 times 12 over 3268760. Calculate that, and we are left with a very small number. That is 0.002625-ish, right? What does that actually mean? Well, the interesting thing is that fractions can be represented as percent chances, right? So let's take this decimal point, move it over 2, and say if the drawing for student council was truly random, given that there are this many ways to get a random student council, or this many unique student councils that we can get, and we had to pick from this pool to get this specific outcome that we're looking at, that means there is a 0.26%-ish chance that this student council was randomly assigned, which I don't know if you realize this, but that is tiny. And I think anybody who wanted to accuse the gamers of doing a little bit of, I don't know, gaming the system, if you will, might have some grounds to stand on. So that is the basics of combinatorics. That should give you everything that you need to accomplish the homework or basically understand the topic, how we get these probabilities, how we're checking these things, all sorts of stuff. And so we can come back here to the front and we can check that third Tommy triple off. Just to review, we covered total probability, which is the idea that the probability of A intersect B is equal to the probability of A plus the probability of B minus the probability of A union B, and vice versa for intersect and union. We talked about this dartboard with the universal set and the intuition behind that. For independence, we recognize that that if A and B are independent, then the probability of A intersect B is equal to the probability of A times the probability of B. And if this equation is not true, the two events are not independent, the intuition we learned is that if you tell me something about A and it is independent from B, then you have told me nothing new about B that I did not know before. If the two are not independent, then tell me something about A, and I now know a little bit more about B that I didn't know before. My information has changed, all right? And then, of course, for Combinatorics Basics, we just covered this general format, this n pick k into n factorial over k factorial times n minus k factorial. And we did a couple of little examples to show you the intuition behind that, whether we were picking groups of boxes or whether we were assigning gamers and ballers to spots in the student council. So hopefully this little mini lecture is going to be a good use of 20 minutes of your time. Hopefully it saves you time if you weren't able to make it to lab hours, or if you were just missing it, or if you just want to supplement your homework or just want to do some learning off on the side if you're not actually in the class. If you are in the class, hopefully we'll see you later at our next class for the next lecture. The next lecture is going to be on conditional probabilities, and so the next mini lecture will also be on conditional probabilities. That will come out on Monday. Thank you so much for stopping by lab hours. I hope you come by for the next one. I hope this was a good and useful stop here at my lab, and thank you so much. Don't forget to subscribe. These will come out pretty regularly if you're interested in that kind of stuff. So thank you so much for watching. Give it a like, give it a comment if you have any questions, or if you have any other questions. If you're in the class, email me at teamorg.ta@gmail.com. If you're not in the class, email me at labhours@teamorg.org with any questions, or you can just leave them in the comments. Again, thank you so much for watching. Have a wonderful day. Thanks for stopping by.